applications of calculus is finding maxima and minima of things. We did that in calculus 1, right? Where's the peak of a curve? Where's the valley, the bottom of the valley of a curve? What if the curve is generalized to a surface? Where's the peak of a surface? Where's the bottom of a valley of a surface? That's what we're going to be about today. Finding local extrema and global extrema of z equals f of x, y, a function of two variables. So you're finding the top or bottom of a surface locally or globally. Well, we'll say this, it's in complete analogy to calculus 1. F of x, y is said to have a local minimum at x0, y0. If it's defined in a disk this time instead of an interval about the point. And f of x0, y0 is less than or equal to f at every other point in the little disk. Alternatively, it's a local maximum if f at x0, y0 is greater than or equal to f of xy at every other xy in the disk. So in either case, we'll say it has a local extremum. Just like calculus 1, you're just doing it over a little disk in the xy plane. Here's a little disk. You have a maximum, and over the image of that disk, the maximum z-coordinate is at x0, y0. In comparison with calculus 1, where you take a little interval and the top of the curve is the maximum over the interval, over some small interval on the x-axis. All right, so then how do we go about finding those local maxima and minima on a curve? We found out a nice theorem was that every local max and min occurred at a critical point. A value of x that had the first derivative of the function equal to 0 or not exist, right? There's two critical points. Similarly, in calculus now, we'll say there's a nice theorem that says every critical point of a function of two variables, every local maximum or minimum of a function of two variables occurs at a critical point, where a critical point is generalized. Either the partial with respect to x is 0 doesn't exist, and the partial with respect to y is 0 or doesn't exist. So the critical point will have both these things, that each of the partial derivatives will either be 0 or doesn't exist. All right. So just like calculus 1, you said, well, once I have narrowed down my places to look for a local maximum by just restricting to looking at critical points, how can I then tell which one correspond to a local maximum? Not every local maximum occurs at a critical point. Some critical points, for instance, you have where they come up like that, and you'd have a flat spot that you go down on one side, up on the other of the curve. Similarly here, with a function of two variables, not every local maximum occurs at a critical point. Here's a bowl-shaped surface, and if you take the tangent plane, there's a local minimum where it just touches this tangent plane at the bottom. Here's a bowl-shaped down surface, has a local maximum at the top where the tangent plane just touches it. But now here's a saddle point, right? This is our hyperbolic paraboloid. And there's a tangent plane right at the seat of the saddle here, but you go up in this direction, you go down in this direction. So the critical point yields neither a relative max nor a relative min, because depending on which direction you go from the critical point, you might go up or down. Well, in calculus 1, the first thing you do is you introduced a first derivative test. If the first derivative is negative on one side, positive on the other, a continuous function at a critical point, then you could say whether if it's negative on one on the left and positive on the left and negative on the right, then you had a local max. If it's negative on the left, positive on the right, you had a local min. No such luck here because of this kind of behavior of saddle points. You have to check all these different directions. You can do that kind of analogy, but we'll just say it's on an ad hoc basis, and we won't do a corresponding first derivative test here. Instead, we'll say in calculus 1 you also had a second derivative test. That way you didn't have to check all around to see if it was a local min or max. You just checked the second derivative at the point. If the second derivative was positive, you decided, oh, second derivative positive, it must be kind of concave up, and so it's a local min. Second derivative negative at the point, then maybe it's concave down around there, so it must be a local max, was the concept. You only had to have the second derivative actually evaluated at the point. You didn't actually have to have the concavity over an interval like that. And you knew it was a local maximum, and just by checking the point. Similarly here, for a function of two variables, we'll have a second derivative test where you just have to check at the point. You don't have to check all around. And that'll be a lot easier than trying to do an analogy to the first derivative test. So for a critical point, here's a nice theorem coming up. For a critical point, x0, y0, at which the two partial derivatives are both 0. So, remember the drawback to the second derivative test was that you have to have the second derivative exist, which means you have to throw out the case where the first derivative didn't exist. This will only be points, critical points, where the first derivatives are both equal to 0. You don't have to worry about the derivative not existing here. You can't apply the second derivative test to those. Suppose those are 0, and suppose the second derivatives exist. fxx, fyy, and fxy, the mixed partial derivative, which is, and they all exist near in some open little disk, no matter how small that x0, y0, in which case, remember our mixed partials theorem, if you have a little open disk near a point on which fxy exists, then fyx is equal to fxy, so you can do it, you can take the second partial derivative with respect to x and y, or with respect to y and x. Either order gives you the same result. Given that's the case, you can calculate d equals fxx fyy minus fxy squared. So second partial with respect to x and second partial with respect to y minus the mixed partial squared, with these taken in either order. And that is going to help you figure out whether it's a local mix, min, max, or neither in most cases. Suppose d at the point, you only have to evaluate it at the point, is positive. Then if the second partial with respect to x is positive, it's a local minimum. Wait a minute, second derivative positive is a minimum? Yeah, it's just like calculus 1. Second derivative positive was concave up, so it's a minimum. Same thing here. If the second partial with respect to x is positive, then it's a minimum. Wait a minute, what if the second partial with respect to y is negative? No. D greater than 0 constrains the second partials in all directions with respect to x, with respect to y, with second directional derivative, all to be the same sign. So if d is positive, then all the directional derivatives are the same sign. fxx greater than 0 implies they're all greater than 0, and you have that bowl shape up. You have a local minimum for your surface. If d is positive and fxx is less than 0, or if fyy is less than 0, or any second directional derivative is less than 0, you'll have a bowl shape down. D greater than 0 constrains all the second partials to have the same sign. So you have a local maximum, right? If one second derivative is negative, they'll all be negative, and you have a local maximum. But if d is less than 0, that tells you that actually that the second partials change sign as you go around. Then you know it's a saddle point, like the hyperbolic paraboloid I showed you. Neither a local max or a local min. And then left out what I didn't write here is if d is equal 0, the test fails. It's just like the second derivative test in calculus 1. In that case, you just don't know anything. It could be a local max, a local min, or neither, and you just have to do some other test. Alright, so I wrote that down. Here's an example. Suppose I consider this nice, easy polynomial function in two variables. X cubed plus 2xy minus 2y squared minus 10x. And I want to find all the local extrema and the saddle points of this thing. Well, how do I do it? I first narrow down my places to look by finding the critical points. That's where both first partial derivatives have to vanish. Remember, if we're going to apply the second derivative test, we don't have to worry about these things not existing. So we'll set both partial derivatives to 0. That means taking the partial derivatives, 3x squared plus 2y minus 10 equals 0, and 2x minus 4y equals 0. Now, once we have the critical points, we have to check each of them with the second derivative, and then we have to solve these. If you put these two equations together, and this is one of the difficult parts, there is no general test for solving two nonlinear equation and two unknowns. This in general is quite hard. Just use by hook or by crook, whatever methods you have from algebra and everything else. These two equations, and often what you do is you'll substitute from one equation into the other. Like in the second equation, you can solve for x is equal to 2y in the second equation, put it into the first equation, and now you find from the first equation, let's see, is this the right one? Yeah, that 12y squared plus 2y minus 10 equals 0. That's a quadratic equation in y, so we can apply the quadratic formula and find that y has two solutions, minus 1 or 5/6. Then plug both of those back into the first equation, and you get either y equals minus 1 with x equals minus 2, or y equals 5/6 with x equals 5/3. That gives two critical points by solving the two equations and two unknowns. These are the only two ways you can get a critical point, make both first partial derivatives equal to 0. Now, once you have narrowed it down to just these 2 points, you just apply the second derivative test to each point. So you take the second partials, fxx is equal to 6x, fyy is minus 4, fxy is 2, and you plug in these points. First the 5/3, 5/6 point, you plug that in and you find out that fxx at that point times fyy at that point minus fxy squared is negative 44 is negative. Remember, if d is negative, that says this point is a saddle point. So there's a saddle point at 5/3, 5/6 that you found. Maybe there's a min or max still. At minus 2 minus 1, I plug that into the second partials. Fxx is 6 times minus 2, fyy is minus 4, fxy is 2. You calculate that, you get plus 44 at this point. So d is positive, we're going to have a local max or min, provided we can get a second derivative negative or positive. The easiest one is to look at fyy. It's already calculated as negative 4, that's negative. And so, negative second derivative, right? It must be a local maximum. So there's a local maximum at minus 2 minus 1. Again, the maximum is the value of the dependent variable. So you plug minus 2 minus 1 into the original function to find the actual maximum value. Z is the maximum value. It occurs at minus 2 minus 1 of f of minus 2 minus 1 equals, I didn't finish it on there. All right. Whatever it comes out to be. And then there's a saddle point at 5/3, 5/6. That's not a local max or a local min. All right, now, what about global max and min? You know, like here's a surface, and it actually has a top point, right? What we'll do is say this. There's a theorem corresponding to calculus 1. Remember, if you had a continuous function on a closed interval, then it took on a maximum value and a minimum value, right? Similarly here, we'll say I have a function on a closed bounded plane region, meaning it doesn't go out to infinity, that's bounded, and it's closed, it includes its boundary. So like this disk, is this hump here is defined over a disk in its interior, a closed bounded region in the xy plane. Suppose this is the function, z equals 1 over 1 plus x squared plus y squared. I want to find the maximum value and minimum value over that thing. Well, the theorem is that a global maximum and global minimum exists of a continuous function of two variables over a closed bounded plane region. And where global maximum means that f at x0, y0 is greater than or equal to f of xy over the entire domain of the function. Right? And minimum correspondingly less than or equal to. Alright, so here's the calculus 1 analogy. Closed interval continuous function. It has a max and a min. It could occur at an interior critical point, or it could occur at an endpoint. Similarly, for a surface over, say, this closed bounded plane region, it takes on a global maximum. It might be at an interior critical point to the square here, or whatever plane region this is, or it might be along the boundary like that, right? So it's the same concept for a function of two variables over a closed bounded region. Either the min and max both occur, and they occur either along a boundary point or at an interior critical point. So here's the function, 1 over 1 plus x squared plus y squared. over the square, minus 3 to 3 for x, minus 5 to 5, I'm sorry, rectangle, minus 5 to 5 for y. Find the global extrema in any saddle point. So you set the partial derivative with respect to x and y equal to 0 to find the critical points, the interior critical points. Here's the partial with respect to x and y, and you find out that this requires x and y both to be 0 by setting these both equal to 0, right? In order for this quotient to be 0, the numerator has to be 0. You know, even though the denominator is complicated, that means minus 2x equals 0, so x is 0. Here's the partial with respect to y. If you set that equal to 0, that means the numerator has to be 0. Y is 0, so 0, 0 is the only critical point. Now check all along the boundaries. The boundary is the hardest part, actually. What you can do is write parametric curves for the boundary along this bottom curve when y is minus 5 and x goes from minus 3 to 3. You set x equal t and y equals minus 5, t going from minus 3 to 3. And along that curve C1, you set g of t equal the function f of x of t, y of t, with x and t given parametrically as a function of t. That makes this curve a function of t only. It's 1 over 1 plus, instead of x squared, t squared. Instead of y squared, it's minus 5 squared. T going from minus 3 to 3. Now you've got a function of one variable. You apply calculus 1 to find what's the maximum and minimum by setting the derivative of g of t, the function of one variable, equal to 0. Well, that says minus 2t over t squared plus 36 squared is equal to 0, right? Derivative of this function equal to 0 says that the numerator has to be equal to 0, says that t equals 0. So there's one critical point at t equals 0 along this boundary. That occurs, let's see, at the corner, right? That was t equal, no, let's see, t equal from minus 3 to 3. It occurs at the middle of the bottom, right? Similarly along C2, you can, that's this one, you can set x equal 3 and y equal t and let t run from minus 5 to 5, sweep out this boundary. Then f, evaluated as a function of t, is 1 over 3 times 1 over 1 plus 3 squared plus t squared is 1 over t squared plus 10. And you find this function of 1, set the derivative of this function of 1 variable equal to 0. You find there's a critical point at 3, 0. That's right here. And you find similarly there's a critical point in the middle of each boundary. Now here's how you find the max and minimum. Just like in calculus 1, you just plug in all the candidate points, see which one makes the f the biggest, see which one makes f the smallest, and you're done. So I plug in the 4 points here on the boundary where there were critical points along the boundary, the one interior critical point at 0, and let's see. Here's at 0 we get 1, at 0 minus 5 we get 1/26, at this one we get 1/10, at this one we get 1/35. Evidently the largest value is 1, that occurred at the interior critical point 0, 0, and the smallest, the global minimum, was at 1/35, that occurred at actually 2. Oh, I'm sorry, I forgot to mention you got to check the corners too, right? Because those are the endpoints of the intervals. We check the critical points of the intervals and the endpoints of the intervals, a la calculus 1, and then we check the interior critical point of the region, and now we find that actually the minimum is at a corner, 1/35. At all 4 corners is 1/35. So you check all along the boundaries and the interior critical points. That's how it works.